So this is a progress check on my new computer, and it is very, very, very close to being completed. I had made a short kind of showing my progress up to this point and kind of just quickly explaining what all these parts are, but I want to go a little more in depth with them. So let's talk about the major parts of this computer. Well, we have my registers right here, which are like my immediate memory. They're the values I am working with right now. If there are values that I'm not working with, I would store them into the RAM in this gray right here. And so this is where I hold values that I want to store for later, or if I need to store many, many, many values, I would put them into RAM. So it's very useful. This is 512 bytes of RAM. Last time I only had 256, and hopefully this should be much faster. Then in this lime green right here, we have my ALU, and this basically just does the math for my computer. It has 12 different functions total, so it can do a large variety of operations. Then down here in this yellow, we have my stack/program counter. Now the program counter is pretty self-explanatory. It just counts which step I'm on for the program, but there's a lot of wires here. But what does the stack actually do? Well, if we see here, if I just go through here, it's actually connected up to the output of the program counter. And so what the stack does is it will hold on to your current program step, or technically one after your program step. And so that way you can make these special jumps called call functions, and so you can jump to other parts of the program, but save where you last were. And so then by using a return function, the stack will spit out the last step that you were on, and you can jump back to there. So that is very important, especially when you make functions, which are sections of repeatable code. Now, of course, that is not everything in this computer. I named 4 colors, but there's a lot more than that. So let me kind of explain what all of this mess is. So as I've mentioned before, most of what goes on in a computer is moving bytes around. So the first thing I thought was, well, let me gather all of the things I can move around. So I got all of the signals for all of the registers. So I gathered the enable ones together and the setting ones together. And for those who don't know, when you set a register, is to store a value to it, and when you enable a register, you read, you open, you display the value that is stored in it. And so then by enabling one register and setting another register, you can effectively move a value from one register to another. But just these lines was not enough. I could, stick levers on them, and I could do this manually, but this is a computer. It's supposed to be all automatic. This is not my goal here. So what I did was I hooked them up to 2 decoders, so a set decoder and an enable decoder. Now, just quickly for those who don't know, a decoder can basically just take a binary number, so a binary number, 1, 1, 0, 1, 1, all the way up to 1, 1, 1, 1 in this case, and it can turn on a certain line. It can decode a binary number. So I can effectively have an ID for every single register. And so then by either putting it into the set or the enable, I can either set or enable that specific register. Now we see that this line is off, which means it's on, and that is the register set. But we see that no signal is actually coming out, and that is because of these torches. And so right now, while these lines, like this line and this line, are off, it is not actually doing anything. So if I turn on this line, though, it allows the signal to escape. And so this way, by briefly unlocking and locking these outputs, I can unlock and lock a register, a particular register. So then I can give the set decoder and the enable decoder both an ID, and then it will move a byte. But right now it's very scattered. We have the input on this side for the enable, and the input on this side for the set. So what I did was I just gathered them together and brought them out front. So we have these 8 bits now control the set and enable. So if I were to, just for an example, for the set I can give 1, 0, 1, 0, which is 10, and then for the enable I can give it a 1, 0, 0, 1. And we can just check this. We can go over here. We can see that the set has a 1, 0, 1, 0, which is unlocking the temporary register, which just holds the value for an operation. So if I were adding 2 numbers, I would give it the first number and store it to the temporary register, and then grab the other number. And then we can see that 1001 unlocks the accumulator, which is just the output of the ALU, the output of the math problem, the answer. This would work, right? I can just leave these here, and then I can hook up some sort of signal that increments the counter each time, and so that way I can have a fully functioning computer. The only issue is that not every function in a computer is a move function, though it is very, very important. So how do I distinguish between these functions? Well, this is where my main control unit comes in. So let's talk about it. Right here, this is, as I said, my major control unit. And so it is controlled by these 4 bits. And 2 weeks ago I made a video talking about how I wanted to structure my machine code, and I decided to section off 4 of the 16 possible bits for my function. So we see here that it uses a decoder, just like the set and the enable over there, and it also makes use of an encoder. An encoder takes a single line, a single redstone line, and breaks it up into multiple signals. So if I were to do my move function, we can see that this line now turns off because it detects it, turns this line off, and we can see that these two torches, these two signals are now on, which is the enable and the set. Let me briefly talk about the functions I have and what all of these signals are for. So I have the move function, which moves data within a computer. We have the load function, which moves data into the computer. We have the jump function, which jumps to a certain spot in the program. Then we have the input and the output, pretty self-explanatory. We have the call, which basically jumps to another step but saves the current step that you're on. And then the return goes back to that step. So then I can interrupt a sequence of steps with a call function, jump to somewhere else and run some code, and then run a return function to pick up exactly where I left off. And then there's the jump if, which is the same as the jump function, but it is conditional, almost like an if statement. If this, then that. Now we have my signal. So what do all of these signals do? Well, we have the jump if and jump, which do exactly what the functions do. It's very automated here. Then we have the load, which is part of the load function, but doesn't actually do the whole thing. All this does is it takes these 8 bits here and allows them to be sent into the computer. Like I said before, a load function moves data into a computer. And then I go over here, we have call and return, exactly same as the functions. And then we have enable, alternative set, and set. Now, the enable and the set go together. It's actually what I was talking about earlier. And these just unlock these little redstone lines with the torches on them and just allows the signal to go out. So that allows me to enable and set whichever register is given in these decoders, whichever ID is put into the decoders. But this alternative set is a little weird. What does that actually mean? Well, it is used for the load function. And so why do I need alternative setting for this load function? Well, normally the set bits are these top 4, but if I'm loading using these 8 bits as the data, I need to use another 4 bits to give my set register, my set ID. And so because right here we have 4 plus 8, that's 12 bits, I have an extra 4 bits that I can use. So I'm going to use the other 4 bits, which right now I just have over there, for the setting. So we can follow this line, goes down here, and all the way over here. So there's this little lock, this little latch right here. So we see normally it allows, because this is off, it allows these top 4 bits to go into the setting. And then we see the alternative bits are locked. But if I were to power this line, we see that it is actually reversed. We see that the normal path is blocked and the alternative set is now unlocked. So the alternative set is effectively just a switch. One more thing before the end of the video, I have modified my program memory. So I basically just took the back half of this side and brought it over to this side. So that did shave off a lot more time. It's 31 ticks now instead of 38, I believe. Now this has shaved off about half a second of total time, but because it has to reach so far, if I was entering the inputs and getting the outputs from right there, it would be about a second and a half faster. But of course I do need to bring it out here, so that does take a little more time just because of the distance. But this is going to be my new arrangement. It's still 2048 instruction steps, but this is what I will be using and what I will be attaching to my computer over there. So that was the update on my computer, just how it's been going so far. I'll probably be done in around 2 weeks, and I'll make a video then. Next week I will make a video giving just talking about the additions, the new things I added on since this video, and talking a little more in depth about how this all works. So stay tuned for those. But that's all for now. Peace.